Hello friends, welcome to this session. Today we are going to see numerical examples on adequacy of rain gauge stations and estimation of missing data. Let's see regarding the rain gauge network first. What is network density? Since the catching area of a rain gauge is very small compared to the areal extent of a storm, it is obvious that to get a representative picture of storm over a catchment, the number of rain gauges should be as large as possible. That is, the catchment area per gauge should be small. On the other hand, economic considerations to a large extent and other considerations such as topography, accessibility, etc., to some extent restrict the number of gauges to be maintained. Hence, one aims at optimum density of gauges from which reasonably accurate information about the storms can be obtained. The word Meteorological Organizations, abbreviated as WMO, recommends the following densities for flat regions of temperate and Mediterranean and tropical zones. Ideal one station for 600 to 900 square kilometer. Acceptable one station for 900 to 3000 square kilometer. In mountainous regions of temperate, Mediterranean and tropical zones, ideal one station for 100 to 250 square kilometer. Acceptable one station for 25 to 1000 square kilometer. In arid or polar zones, one station for 1500 to 10,000 kilometer square depending on the feasibility. 10% of rain gauge station should be equipped with self-recording gauges to know the intensities of rainfall. From the practical considerations of Indian conditions, the Indian standard IS 4987-1968 recommends the following densities as sufficient. In plains, one station for 520 square kilometer. In regions of average elevations of 1000 meter, one station per 260 to 390 square kilometer, and predominantly hairy areas with heavy rainfall, one station per 130 square kilometer. Now let's see some formulation regarding the adequacy of rain gauge stations. If there are already some rain gauge stations in the catchment, the optimal number of stations that should exist to have an assigned percentage of error in the estimation of mean rainfall is obtained by the statistical analysis as n is equal to in bracket CV divided by E bracket square, where n is optimal number of stations, is allowable degrees of error in the estimate of mean rainfall, CV coefficient of variation of the rainfall values at the existing M stations in percent. If there are M stations in the catchment, each recording rainfall values P1, P2, Pi to Pm is in a known time. The coefficient of variation CV is calculated as CV is equal to 100 into summation m minus n divided by P bar. Okay, so this summation or sigma m minus 1 is calculated with this formula under root. Okay, this summation of Pi minus P bar bracket square divided by m minus 1. Okay, root of that. This is a standard deviation. Pi is nothing but the precipitation magnitude in ith session. P bar is equal to 1 by m into bracket summation of Pi, which is a mean precipitation. Okay, so remember, number of values of precipitations are given for a station, and from those values you can find out the standard deviation. Okay, where mean precipitation. Now here the formulation of the statistics is comes in the picture. Now consider the existing M rain gauges. They have a mean rainfall of P and a coefficient of variation CV. To know the percentage of error EEX of estimation of mean in the existing system of M rain gauges can be rewritten by changing N by M as M is equal to under root CV divided by EX, E to suffix, EX is to suffix, bracket square. So EX is equal to CV divided by under root M. Okay, so remember this, it is a percentage of error EX of estimation of a mean in the existing system of M rain gauges. In the above rain gauges, the term EEX represents the expected error in the percentage in the estimation of mean P. It is a measure of the accuracy of estimation of mean precipitation in the existing system and is called standard error in the estimation of the mean. In calculating the number of rain gauges N for given level of error by using equation, it is usual to take EEX as 10%. It is seen that if the value of EEX is small, the number of rain gauges required will be more. According to the WMO recommendation, at least 10% of total rain gauges should be of self-recording type, as we have seen earlier. Now let us see one example. Example 1 is a catchment of 6 rain gauge stations. In a year, the annual rainfall recorded by the gauges are as follows. Now here the stations are given A, B, C, D, E, F. Okay, rainfall of every station is given in the centimeter. For A it is 82.6, for B it is 102.9, for C it is 180.3, for D it is 110.3, for E 98.8, for F 136.7. What we have to determine? First one, determine the standard error in the estimation of mean rainfall in the existing set of rain gauges. Second, for a 10% of error in the estimation of the mean rainfall, calculate the optimum number of rain gauge stations in the catchment. Okay, now here remember this formulation we are going to use for the CV, the formula that we have seen. Okay, where the CV is the coefficient of variation, and this formula we are going to 100 into summation m minus 1 divided by p bar, and here this value, the summation m minus, which is a standard deviation that we have seen the formula under root, okay, pi minus p bar bracket square divided by m minus 1. So from this formula we can find out the standard deviation, where the pi stands for the precipitation of magnitude in the ith position, and p bar is 1 by m in the bracket summation of pi, which is a mean precipitation. So from the calculator, this direct value you can calculate because the statistical inputs are there in the scientific calculator. Now for this given data, number of rain gauges are 6, m is equal to 6, value of m is 6. Mean annual rainfall p bar is calculated, so mean of this calculator is 118.6, okay, which is a standard. Then from by using this formula, summation m minus 1, it is calculated as a 35.04 centimeter. Okay, as you can directly calculate by using the statistical inputs of the calculator, you can find out this value. Then as I told, by using this particular formula you can find out the coefficient of variation CV equal to 100 into summation sigma m minus 1 divided by p bar is equal to 100 into calculated value of this 35.04 divided by mean annual rainfall 118.6. You are going to get coefficient of variation is 29.54. The first one, now let us answer the questions. First one is the standard error in the estimation of the mean, which is EEX, and the formula is CV divided by under root M. So that is equal to this calculated value of coefficient of variation CV, that will come here 29.54 under root number of rain gauge stations are 6, M is equal to 6 under root 6 is equal to 12.06%. Okay, and the second question is for 10% of error in the estimation of the mean rainfall, calculate the optimum number of rain gauge stations in the catchment. So when the error is limited to 10%, E is equal to 10, and the optimum number of rain gauges given in the catchment by the formula N is equal to in bracket CV divided by E bracket square, that is equal to 29.54 divided by 10 bracket square, that is equal to 8.73, that is equal to 8.73. Hence optimum number of rain gauges is 9 rain gauges, and thus number of additional rain gauges required is equal to 9 by 9 minus 6 is equal to 3. So 3 additional rain gauges are required. So such a very simple formulation is there, that you have to remember this formulation, and very important to calculate the standard deviation. Next one will to see the estimation of the missing data. In the estimation of missing data from a rain gauge stations, performance of a group of neighboring stations including the one missing data are considered. A comparison of recordings of these stations are made by using their normal rainfall as standard comparison. The normal rainfall is the average value of rainfall at a particular date, month or year over a specified 30-year period. The 30-year period is normal, is recomputed every decade. Thus the term normal annual precipitation at station A means the average annual precipitation at a station A based on specified 30-year of record. Now what is the procedure to find out a missing data, or you can say procedure of missing data estimation? What is first? Statement of missing data problem. Given annual precipitation values as P1, P2, P3 up to Pm at neighboring M stations 1, 2, 3 to M respectively. It is required to find the missing annual precipitation Px at station X not included in the above M stations. Further, the normal annual precipitations N1, N2, Ni at each of the above M plus 1 stations including the station X are known. Okay, so precipitations are given. Okay, and this annual precipitations are also this M plus 1 station included, these are known. What is procedure? First one, if the normal and annual precipitations at various stations are within about 10% of the normal annual precipitation at X station X, then simple arithmetical average procedure is followed to estimate Px. Thus Px is equal to 1 by M under in bracket P1 plus P2 up to Pm. Okay, bracket complete. Okay, where this P1, P2, P2, these are the precipitation values. Second, here If the normal annual precipitations vary considerably, then Px is estimated by weighing the precipitation at various stations by the ratios of normal annual precipitations. This method, known as the normal ratio method, gives Px as Px is equal to Nx divided by M in bracket P1 divided by N1 plus P2 divided by N2 plus so on Pm divided by Nm bracket complete. So remember these two formulations here. Now let us see the example, very simple one. The normal annual rainfall at stations A, B, C and D in a basin are 80.97, 67.59, 76.28 and 92.01 centimeter respectively. In the year 1985, the station D was inoperative and the stations A, B and C recorded annual precipitation of 91.11, 72.23 and 79.89 centimeter respectively. Estimate the rainfall at station D in that year. Okay, so we'll have to keep this keen observation on this normal annual rainfall at the all four stations. The four values are given respectively. But what happened in the year 1985? The station D that was inoperative and ABC recorded these three values. Okay, so what is our target? To estimate the rainfall in 1985 of station D. So let us see maximum difference in normal rainfall values from the normal value at a station. Okay, so what is the maximum value and what is the minimum value of those particular given values? 92.01 is the highest one and 67.59 is the lowest. So maximum difference is 24.42 centimeter. So percentage maximum difference with respect to normal at the station is D is equal to 24.42 divided by the 92.01 into 100 is equal to 26.54. Okay, this is the maximum percentage, you can say maximum difference. As the normal rainfall values of the surrounding stations vary considerably more than 10%, the normal method is adopted. In the normal ratio method, M is equal to 3. Using estimated rainfall at the station D is equal to PD, which is equal to ND divided by 3 in bracket PA divided by NA plus PB divided by NB plus PC divided by NC bracket complete. So PD is equal to 92.01 divided by 3. Okay, so 92.01, okay, this value and in the bracket 91.11 the values which are obtained in the 1985, 72.23 divided by, you can see, 80.97 here, then 67.59 this value and 79.89 divided by 76.28 bracket complete. So solving this, 30.67 value of this into bracket, this value is calculated, sum of that multiplied by that. So estimated rainfall at the station D, PD is equal to 99.49 centimeter, supposed to be in the 1985. So very simple examples are there, but you will have to remember the formulation, okay, and the method of calculation. So that's all from today's session. So we'll stop here, meet you in the next lecture.